All right, Chemistry 3101. We're going to start this morning off with a little bit of Chapter 8 review. Just start by reviewing some of the reactions. Here we have a compound. This is 1-methyl cyclopentene, so it's an alkene. That's the whole point of Chapter 8 is we're looking at addition reactions of alkenes. And I just have a smattering, or there is a smattering of reagents here, and we're going to try to figure out what the products would be. And again, this is really, a lot of this is pure memorization, I would say, because some of these reactions we did, actually in all of these cases, I'd say we looked at the mechanism, except for maybe the first one, okay? The first one, which is treating your alkene with potassium permanganate and sodium hydroxide and keeping it cold. And that cold just means colder than room temperature. It might be 0 degrees, it might be 10 degrees Celsius. That's neither here nor there. But this reaction is a dihydroxylation, right? That's the whole point of this. We did a whole section on dihydroxylation. And what occurs here is that you get syn. You get syn dihydroxylation. Now, what does syn mean? It means that both of the hydroxyls are going to be added to the same face of the molecule. So I'm going to start by drawing the 5-membered ring like this, and I'm going to put one of the hydroxyls pointing up. So that means the other hydroxyl is going to be pointing up like this, which would mean that this methyl group must be going down. So I'll try to draw the best dash I can like that. And I'm also going to have the other compound where both hydroxyls would be pointing down and the methyl group would be pointing up. So that would be switching every stereocenter. So that means it's the enantiomer. If you remember in Chapter 5, we talked about how if you were to invert every single stereocenter, you're essentially producing the enantiomer. So that's what we would get, would be the enantiomer. I have a question for you guys about the next one. We're going to go counterclockwise here. So now we're getting, or sorry, clockwise. Rather, we're going with HCl. So could anybody tell me, if I just took this molecule, just a plain old cyclic alkene, it's not symmetrical, is it? Right, we've got a methyl group over here. Here we've got a hydrogen. Would this be a Markovnikov or anti-Markovnikov addition? Could anybody tell me? And it's not a trying to fool you or mix you up or anything. Just practice. Yes, absolutely. Yes, I see. All my students, Edwin, Jonathan, you're all 100% correct. It would be a Markovnikov addition, right? So we'll write here, this is Markovnikov addition. We'll leave it like that. So what are we going to do? Remember, the rich get richer. There is a proton here. So that is the carbon that's going to take the new proton, right, from our HCl. So let's write it down like this. So now this carbon has 2 protons. I'm going to leave them out because this is a bond line structure. So I'll just delete those. But then we're going to have our chlorine and our methyl group here like that. And I'm going to move this over just to make it a little tidier. But the reason why, if you're wondering, like, why isn't the chlorine like pointing up or pointing down? Why didn't you indicate that? The reason why is because this carbon is not a stereocenter, right? Stereocenter. Remember that the pathway from this carbon going this way or this way, it's identical, right? There's a plane of symmetry in the molecule, and when there's no stereocenter, I don't have to indicate if the chlorine is going up or if the methyl group's going up or anything like that. Don't need to worry about that. All right, I have a question for you guys about the next one. The next one is a hydrogenation reaction. I never really talked to you a lot about the dangers of hydrogenation. You think about it, you're using hydrogen gas, you know. I'm sure you've all heard of the Hindenburg, which was a big explosion of this Zeppelin or airship that occurred in Lakehurst, New Jersey in 1936. Anyhow, hydrogenation can be a very dangerous reaction, although we have ways to mitigate the danger of that reaction. But my question to you is, if I take my alkene and I subject it to hydrogen gas and platinum, and it could be palladium, it could be nickel, would this produce a syn addition or an anti addition of the hydrogen? Does anybody remember? I talked about the mechanism briefly with you one day. I talked about how the hydrogen gets absorbed to the catalyst. I said your molecule is almost like a UFO. So hydrogenation occurs with the syn addition, okay? So hydrogenation, we'll write it down here, hydrogenation occurs with syn addition, okay? I don't know why I put quotations up here. There's no need for that. But it occurs with syn addition. Yes, so it's all the hydrogens both get added to the same side. okay? Now we're going to add a hydrogen to this carbon and to this carbon too. But the thing is, the fact that it's syn addition doesn't really mean a whole lot in this particular example. Why? Because I end up with methyl cyclopentane, which has no stereocenters. So the fact that it's syn addition is no big deal. I mean, if you're practicing at home, you know, if you're just practicing by yourself, and if you were to write this, if you put the methyl and put the two hydrogens, like if that helps you remember that it's syn addition, that's not a crime, okay? That's not against the law to write in the two hydrogens like that. It's no big deal, but you still have no stereocenters in the molecule. It's like you're indicating stereochemistry where there is none. But again, it's not a big deal. You're learning the subject, right? You're working it out and trying to figure it out and get things straightened out in your mind. So there's nothing wrong with that. All right. The next reaction has kind of a funny name, right? When we take our alkene and we treat it with bromine, Br2, but we're in a solvent, which is water, right? Remember that this is first going to proceed through the bromonium ion. I'm going to do my best to draw a bromonium. I'll draw it with the bromine in the three-membered ring pointing down like this, okay? There we go, like that. Now, if I highlight this carbon in yellow, and if I highlight this carbon in green, when water comes in and attacks this as my nucleophile, could anybody tell me which carbon would the water attack? Would it attack the carbon in yellow or the carbon in green? I went over this in some detail with you. So in this case, and in any case when we're dealing with hydrohalogenation, the water is always going to attack the more hindered carbon. Okay, so the water is actually going to attack, okay, let me draw some lone pairs in here. The water is going to attack the more hindered carbon, like that. Now, if you're wondering, now why would that be? Right, if you remember, the whole rationale was that it's not about sterics, it's about electronics. And it's about which one of these carbons, is it the yellow one or the green one, that would be more comfortable with the partial positive charge, right? Yes, it's going to occur by backside attack. It's going to go from the opposite side of the three-membered ring. But another way you could think about this maybe would be like this. If I was to draw, and you don't have to draw, it's not a resonance structure technically, but if you were to think about a resonance structure like this, right, where you have the bromine over here, then you would have a tertiary carbocation, right? So the yellow carbon is going to be more comfortable with that positive charge, because the other possibility would be to have the methyl group and the bromine here if you were to break this bond, and then you'd have a secondary carbocation. So it's based off of electronics, right? Which carbon is going to produce the more stable carbocation? Okay, so that's another way to think about it. If you go back in our slides, you can see I discussed this in detail with you. So again, the water is going to attack the more hindered carbon. Again, it's going to be attacking from the top face. I know there's a methyl group here. I realize that. However, this three-membered ring is on the bottom face, and that is bigger than this little methyl group here. So the water is going to attack, again, from the top face of the molecule. It's going to crack this open like that. And then what you end up with, I'll draw the final product here. You're going to have your bromine going down like this. You have this methyl group is going to be going down. And then after the proton transfer, of course, you're going to have the hydroxyl pointing up like this. So I'll put a couple of arrows because it's nucleophilic attack and proton transfer. But this is going to be the product. And there's two stereocenters here, isn't there? There's a stereocenter here and a stereocenter there. And so not only are we going to obtain this product, we're also going to obtain the enantiomer, because we're going to invert, have the non-superimposable mirror image. Okay, so this reaction is hydrohalogenation. So this is called halohydrin formation. Sorry, must be my halohydrin formation. Okay, and halohydrin formation is covered in section 8.9. So if you want to review the mechanism and why we get the water coming in as a nucleophile and attacking the more hindered carbon, you could go and take a look at that. All right, so the last one here in this little review question here, this reaction is called oxymercuration, and then demercuration. Okay, it's a two-step process. First step is using mercuric acetate and water, and the second step is using sodium borohydride. So the whole point of oxymercuration, look, as somebody who worked in a lab for most of his life, or a good chunk of his life, I would avoid using mercury anytime I can. Okay, nobody wants to mess around with mercury. It's dangerous. It's hard to get rid of it. You can't just put it in a regular waste container. It's against the law. So it's always a pain in the neck to work with mercury. But the reason why you would do this reaction, right? Sometimes you got to do it. You got to do a tough reaction. And the reason why you would do this reaction is because this reaction will affect a Markov-Nikov addition of water. However, we do what? We avoid carbocation rearrangements. Now, there's no carbocation rearrangement to worry about with this molecule, but it still bears, repetition and practice. So let's draw what the Markov-Nikov product would look like. I'm going to ask you guys a question. If I have this carbon highlighted in yellow and this carbon highlighted in green, where would the hydrogen go? Would it go on the green carbon or the yellow carbon? When I do my Markov-Nikov addition of water, where would the hydrogen go? Green or yellow? Yeah, it's going to be on the green one, right? The rich are going to get richer. That's the whole point behind Markov-Nikov addition. So let me just delete that. There we go. So our hydrogen would go, oops, I didn't mean to do that. Our hydrogen would go on this carbon, and then our hydroxyl is going to be over here. And again, there's no stereocenter, so we don't have to indicate any kind of stereochemistry. All right, there we go. So that question gave us some good review. So you might want to look over or review hydrogenation, halohydrin formation, which is in section 8.9. All right, so halohydrin formation. Well, with all that in mind, let's try some more review questions here. 8.60 just asks us, identify the starting alkene, and it means identify the starting alkene of an ozonolysis reaction, okay? Which is first step is ozone, and second step is DMS, and of course you could use zinc and water too, right? So how would we figure this out? We haven't looked at ketone or aldehyde nomenclature. That's covered in organic chemistry too. But this is formaldehyde, which you've all heard of before, and this is cyclopentanone. So how do you figure this out, right? What alkene would I start with to, treat with ozone and end up with these two carbonyl compounds here, this aldehyde and this ketone? Well, all you have to do is literally take them. So let's draw the formaldehyde molecule. Take the two of them and point them towards each other with the two oxygens pointed towards each other like that. You erase the oxygens, and then you connect the double bonds. This is Mr. Dion's skill builder. And there's your starting alkene. Now that is drawn. It looks ridiculous, but that's the idea. Okay, so I'm just going to erase that. And in terms of retrosynthesis, what you would start with would be simply this alkene. There you go. It's just that. So this is called methylene cyclopentane. All you would do is you would take that and you would treat it with ozone in the first step, and in the second step, you would treat it with DMS. Hey, I have a funny question for you guys. Has anybody here ever made ozone themselves? Has anybody here ever used an ozonizer? They're not that uncommon. You can probably buy one on Amazon, or maybe even at Ace Hardware. I don't know. But has anybody here ever used an ozonizer before? An O3 generator? And you don't have to answer this question, Jessica, but can you tell me what you used it for? And again, if you just want to say no comment, you can just say no comment. Yeah, you don't have to answer my questions, but unless it's a chemistry question. But does anybody know what you would use an ozonizer for? Like, I've used one once. I rented one actually.
So I don't know if it's the same thing, but my husband is at his mom in Idaho, and he just told me that she offered one for a washing machine.
Okay.
Is it the same thing?
I'm not sure if ozonizers are used in a washing machine. I'm not familiar with that. I don't know, but you could be right. It could be used for that. Absolutely. I'm not 100% sure. Jonathan says for fun or something, and somebody else says roommate. So what I used it for is this. I'll tell you a very short story. So maybe 3 years ago or something, my wife and I took our two kids before we had the third one, and we went to Costco, and we came home and our front windows were open. Oh, it is a new thing in washing machines. Well, see, Warren, it's something that I didn't know. I'm learning. I'm gonna have to Google that after class because you guys are teaching me new things, right? That's why it's great to teach post-secondary education. Your students teach you stuff all the time. But anyhow, when we came home, the front windows were open. We had left them open, and there was smoke, black smoke billowing out of the house. I thought the house was on fire. Okay. I had no, I thought the house was literally on fire. And when we came in, what my wife had done is, I shouldn't throw her under the bus, but anyhow, she had left beans boiling on the stove and forgot about it. And they had boiled dry, and the beans, they weren't on fire, but they were burning, my friend. And it just made this smoke. It got all throughout the house. After 2 days of having the windows open, because it was summertime, we could not get the smell out of the house. And so I rented an ozonizer. And you shouldn't be in the house when the ozonizer is running, because it, puts ozone all throughout the house, which is not good to breathe in. You need oxygen, not ozone. But it gets rid of the odors. So that's what I've used it for. And apparently some people use it if they're cigarette smokers. They'll run an ozonizer in their house now and again to get rid of the cigarette smell. So that's, how you produce ozone. Ozonolysis is one of the few reactions in organic chemistry that's common that I've never done. I've never done an ozonolysis in my life, but I worked with a guy who used it all the time in a program he was working on, and we actually had an ozonizer in the lab on a cart, and he would come in, it makes this buzzing sound. Anyhow, so that's how you get ozone, just sharing that with you. And now you guys have taught me about these washing machines that, use ozone. I'm going to have to Google that because I have an inquiring mind. Anyhow, for the next one, we do the exact same exercise, right? We're going to take the first, we'll take the aldehyde here, right? Like this. So this is benzaldehyde. That's what it's called. And then we'll draw, this is acetone, right? And again, this is Mr. Dion's skill builder. And we're just going to connect those bonds like that. The second one, I didn't do a very good job, but that's going to be our starting material. Okay, so let me erase all that and I'll draw it a little bit prettier. So we'll start by drawing the aromatic ring. Here we go. And there we have it, like that. That would be our starting material. Again, step 1, ozone. Step 2, DMS, dimethyl sulfide, which is really stinky. And then the last one, I think hopefully by now you're getting the idea. So yeah, when you're thinking about what starting materials you would need, you'd have to have a 6-membered ring like this connected to a 5-membered ring like that. And that's it. And again, same thing, just repetition. It's like writing lines. If you ever got in trouble in school and had to write lines, you write the same thing over and over, and eventually it'll just it'll stick in your brain, right? Repetition. Okay, let's take a look at 8.63. I went ahead and wrote this down. These are great problems. You could maybe even print this out if you have a printer at home, or you could use an iPad if you have one, and just repeat this question over and over and over. Don't do it in the same order every time, because this question is nothing more than a repetition of the reactions that we learned, just trying to help you remember all the different reactions that we've learned. Now, I'm going to ask you about some of them, but some of them I'll just solve myself. Like this one here. We just saw a reaction very similar to this, right? Where you're going to treat this with ozone. And then in the second step, you're going to treat this with DMS, and that's going to cleave the double bond here. So if you're wondering, like, hey, Mr. Dion, wouldn't I get something else besides cyclopentanone? Yes, you also end up with this compound, which is formaldehyde. They just leave it out. And if you're wondering, like, why do they leave things out like that? Well, formaldehyde is a gas, for one thing, so it probably just bubble out of the reaction mixture. This molecule is a liquid, so they just leave out small molecules out sometimes like that. Okay, so let's go clockwise. Let's try this one here. Could anybody tell me what's going on here to make this compound that I have the blue circle around? Would this be a Markovnikov or anti-Markovnikov addition of HBr? Because we're adding one hydrogen and one bromine. Would this be Markovnikov or anti-Markovnikov? Yes, absolutely. Yes, Mackenzie, thank you. It's an anti-Markovnikov addition, isn't it? And the only way that we know to do anti-Markovnikov addition of HBr across a double bond is to use HBr and a peroxide like that, an organic peroxide, not hydrogen peroxide. That doesn't work. You can't add H2O2, but an organic peroxide. Again, if you want to look ahead in the book, it's not a crime to read the textbook. If you want to look ahead and see the mechanism for that, that's covered in chapter 10, the mechanism. However, the reaction, we do learn it in this class. The next one is an anti-Markovnikov addition of water across a double bond. Well, how do we do that? We know that that's a two-step process. First, we treat the molecule with borane and THF. And then in the second step, we treat it with hydrogen peroxide and sodium hydroxide. So again, these two last reactions, okay, these are both anti-Markovnikov addition, both of them. All right, let's move on. The next one is a dihydroxylation, right? We're adding a hydroxyl to this carbon and to this carbon. There's no stereochemistry to worry about because we're not producing a stereocenter. And so, I mean, to make this molecule, you could choose any of the dihydroxylations that we learned in the class. I mean, you could use MCPBA followed by aqueous acid. That would work. We could write that down. It could be ozonolysis, which is, osmium tetroxide, which is one of my favorites. So let's put that down. We'll put down here OSO4, catalytic. So a catalytic amount of osmium in NMO, which was N-methylmorpholine N-oxide. If you remember, I mentioned an N-oxide briefly. And we'll put here, or we'll try MCPBA followed by hydronium. Either one of those would work. And if you want to put, potassium permanganate, sodium hydroxide, cold temperature, that works too. But this is just a dihydroxylation. The next one is, hold on, it's my computer here. The next one is a halohydrin formation. We looked at that also this morning. We said you would treat the molecule with bromine and water. Notice that the hydroxyl that came from the water, that ended up where? On the most hindered carbon, right? And we talked about that a little bit this morning. Could anybody suggest reaction conditions for the next one, where I have the yellow question mark? Yeah, absolutely. Somebody just wrote H3O plus. Yeah, totally. That's all you need is just adding water to it, right? So this is just nothing more than a Markovnikov addition of water. There's no carbocation rearrangement to worry about. And so here you would just use aqueous acid. So yep, I'll just write that down. H3O plus. Perfect. Again, this is a Markovnikov addition of water. And then the last one is a Markovnikov addition of HBr, right? If you compare the two, I can barely see them here, but you look in the top and I have the product of anti-Markovnikov addition. And then if you look down here, here's the product of Markovnikov addition. And for that, we just use plain old HBr. Okay, there we go. Now we're moving down. There's still some more problems here. So if I want to do this transformation here, this alkene that I have down here, so this is called 1-methylcyclopentene. Would this be the Zaitsev product of elimination, or would this be a Hoffman product, right? Because this is an E2 reaction. Okay, it's an E2 mechanism, but would this be Zaitsev or Hoffman? Could anybody identify that by the last name, the surname of the chemist? Okay. Yeah, so I got a couple of votes here. All right, so this would be the Zaitsev product. Yes, absolutely. Yeah, absolutely. This would be the Zaitsev product. Okay, so let me write that down. Zaitsev. Right, the Hoffman product would be this one, where you have the double bond here. I can draw that a little better. Right, because if you look at this compound, right, this is our alpha carbon here. We have the beta proton here, that type of beta proton, but we also have beta protons here, right? If you pull off the one in black, you end up with the double bond here. And if you pull off the one in blue, you end up with the double bond here. So the one that's pulled off in blue, that gives you the Hofmann product, okay, the Hofmann product. And the one that is more substituted, that is called the Zaitsev product. So if we want to make the Zaitsev product by an E2 reaction, we're going to use what? We're going to use an unhindered base, like sodium ethoxide, or it could be sodium methoxide. We could write that, either one like that. And if you wanted to make the Hofmann product, for that, you would use a hindered base like potassium T-butoxide. All right. Okay. I got a question for you guys. Could anybody suggest a reagent to do this transformation, to go from the alkene to the alkane? Yes, exactly. Thanks, Edwin. Yep, just hydrogenation. So there we go. Hydrogen and platinum, and it could be palladium. It could be nickel. Okay, remember that you could use or palladium or nickel, like that. Remind me to tell you a funny story about catalysis sometime when we have a minute. Let's see. Next one, we're doing a syn dihydroxylation. I mean, you can use whatever conditions you want to do a syn dihydroxylation. We already looked at it a few minutes ago. So syn dihydroxylation, again, my favorite method is to use osmium tetroxide. I know it's dangerous, but if you just use a catalytic amount, you double glove, you put your lab coat, your safety shield, everything, I don't think it's that bad. NMO. And then the last one is an anti-dihydroxylation. So there's only one way that we have to do an anti-dihydroxylation, and that is to first treat the molecule with something like MCPBA. Okay, and if you just want to write this, that's fine too, a peroxy acid. And then in the second step, you treat it with hydronium, like that. All right, there we go. Okie doke. So yeah, that covers those two questions. A lot of good practice there. I mean, again, I think it might be wise to print this problem out and 8.63, and you could just try it over and over and over. That might be a strategy you might want to take. So that leads us to the last question, which was 8.50. I have to find it here. 8.50. Just give me 2 seconds. Okay, 8.50, which is another synthesis problem. All right, so 8.50. There we go. So let's take a look at A. I didn't write any of these down, so we're starting with this molecule. This is called propanol, or 1-propanol, and then we're gonna want to make 2-propanol. This is rubbing alcohol. This one here. Buy that down at Costco. A lot of Costco talk today, but anyhow, you can buy it there. And then we want to do both of these transformations, and I'm going to give you a few minutes to think about that. While you're thinking about that, I'm going to write down B. Okay, let's start with 8.50A. So we'll start with the top one here. We want to take this alcohol and we want to make rubbing alcohol. Well, I think would be the funnest way to do this, the easiest way, is you remember one of my favorite reactions that I told you about was to take any alcohol. If you just heat it up with concentrated sulfuric acid, it's all right, concentrated H2SO4, and heat. What's that going to give you? That's just going to give you the alkene. There's only one regioisomer. I mean, there isn't another regioisomer. But either way, you end up with this molecule, which is propene. And so then all you have to do, if I had propene and I want to make this 2-propanol, or a rubbing alcohol, would this be a Markovnikov addition of water, or an anti-Markovnikov? And it's not a not trying to fool you or anything. Yes. No, oh, sorry. It's a Markovnikov addition, right? Because you have two hydrogens here and only one here, right? So in your final product, you have 1, 2, 3. So the rich is getting richer. So this is a Markovnikov addition of water. So all you'd have to do is treat it with aqueous acid like that, and you would end up with the alcohol in this position, or the hydroxyl in that position, I should say. Okay? Does that make sense? Give me a thumbs up if that makes sense to you. Right, this molecule is so small, you know, you only have one regioisomer whenever you treat it with sulfuric acid. Okay, cool. All right, good. All right, so that's that one. If we want to go from, now we want to take this compound and we want to make this compound. Well, look, if we treat this with concentrated sulfuric acid, so again, just repeating the same thing, there's only one regioisomer, right? If you have 3 carbons, the only possible alkene you can have is this. So you would end up with that alkene. Now, what you want to do is you have the richer carbon, which is this one here. Then you have the poorer carbon that I'll highlight in red. Well, now your hydroxyl is going to end up on the one that's richer in hydrogen. So this is an anti-Markovnikov addition of water. So you would first treat it with borane and THF. And in your third step, you treat it with hydrogen peroxide and sodium hydroxide, right? So that's the whole idea here, okay? So again, this first one was a Markovnikov addition, and these 2 steps are for an anti-Markovnikov addition, just like that. All right, and again, what are we doing? We're just rehashing the same old reactions over and over and over. There's the same like 12 reactions or so that just keep coming up over and over and over. All right, so next we want to get my red pen in again. We want to take this tertiary alkyl bromide and we want to convert it to this secondary alkyl bromide. Well, in terms of retrosynthesis, what I need to have is this alkene, and then I just need to do an anti-Markovnikov addition of HBr to it. So how am I going to go from here to here? Well, I've got 2 types of beta protons. I've got this one here highlighted in red, and I've got this one highlighted in blue. If I want to pull off the one in blue, I'm going to use a non-hindered base like sodium ethoxide or sodium methoxide. It doesn't matter. But then that would give me this alkene. You can see that this carbon is richer in hydrogens, but I want to add the bromine there. So in order to add the bromine to that position, I'm going to do an anti-Markovnikov addition of HBr. So use HBr and a peroxide, like that. Now in terms of going in the reverse direction, so going from the secondary alkyl bromide, okay, and going over here, right, the same type of thing is going to occur because I want to have this alkene again, and then if I have that alkene, to get from here to here is just a Markovnikov addition. So again, if I look at this compound, I've got the proton in red here, and then I've got the proton in blue here. If I pull off the proton in red, I'm going to end up with this alkene. If I pull off the proton in blue, I end up with a regioisomer, which isn't the right one. So to pull off the proton that's in red, I would use a non-hindered base, sodium ethoxide or sodium methoxide. I'll use methoxide this time just to mix it up. And then I'm going to do a Markovnikov addition of HBr. So I just treat the molecule with hydrogen bromide, nothing more than that. Okay, so just kind of moving the atom around the molecule like that. So there's the answer to B. Let's take a look at C. Let me find it here. We'll look at these 2, and then so C is for cookie. Let's see. I've got this molecule, so I've got the chlorine coming up, and the methyl group going down. Then I've got this methyl group going up, and then I've got these 2 methyl groups going up. Like that. Okay. Son of a gun. I end up with, this is a meso compound, isn't it? Right? You got a plane of symmetry through here. So this is a meso compound. Anyhow, how do we do this? Well, whenever I'm faced with a problem and I'm not exactly sure where to start, I always like to start with a retrosynthesis, go backwards and think, well, you know, just in terms of retrosynthesis here, if I had this compound, 1,2-dimethyl cyclohexene, right, all I'd have to do is a hydrogenation, right? And I would get both of the hydrogens added to the same face of the molecule like that, and I would get my meso compound. So then the question becomes, well, how do I make that alkene starting with this alkyl chloride, right? Because there's two types of beta protons. If you look at this molecule carefully, here's your alpha carbon. That means that you've got this beta proton here in red, and then I also have this beta proton in green. Notice that I wrote both of them pointing down. Why did I do that? Because if this chlorine is up and axial, remember that in order to do an E2, the next proton has to be down. Because if it's down, that means that it is also axial, right? And remember that we looked at this in detail earlier on, and this one is down and axial. However, I'm trying to make the double bond between these two carbons. So one of these protons would give me the Zaitsev product, the other one would give me the Hofmann product, but I want to make the Zaitsev product, right? I want to make the most substituted alkene, right? If I made the Hofmann product, that would be this. I would have my double bond over here, okay? And then I would have this methyl group pointing up like that. I don't want to make that compound. I want to make the one that's in blue. And so to pull that proton off, I'm going to use an unhindered base, like sodium ethoxide or sodium methoxide. So let's write that down, sodium ethoxide. That's going to give me the compound in blue. And then I treat that with hydrogenation conditions, and boom shakalaka, I'm done, just like that. All right, let's look at the last one. Again, just more practice on the same old kinds of reactions, but you see why organic chemistry is challenging, because there's so many different ways to ask questions about all these different reagents. We want to take this secondary alcohol. We want to make this this cis-diol, sorry, which is formed via syn addition. Come on. There we go. Anyhow, I think the retrosynthesis here, I think you've probably all got this figured out. All I need to do is make cyclohexene, and then I just do a syn dihydroxylation. So I could use osmium tetroxide, a catalytic amount, and then NMO is my co-oxidant. Well, how would I get from here, from my alcohol to the alkene? I mean, there's no regioisomer to even worry about at all. So I think what I would do is I would just treat it with concentrated H2SO4, right? And heat it up. And that's going to make this alkene. And then in the second step, we just treat it with our osmium tetroxide, a catalytic amount, and we put in N-methylmorpholine and oxide as our co-oxidant. And there you have it. Walla walla bing bang. That's all there is to it. So again, you see how many interesting ways there are to, apply all of the different reactions that we learned in chapter 8. And there's a lot of them. There really are quite a few reactions that are learned in chapter 8. Again, if you go back here in section 8.14, it's got a beautiful review of the addition reactions, and we kind of talked about some strategies that we could use to learn all these different reactions. I think flashcards, repetition is a good idea. For me, when I was where you are, when I was studying, and I'm still studying organic chemistry, but I find that just practice, looking at a problem and literally, borderline hitting my head against the wall before I would look up an answer or anything. That's how I like to do it. I just like to practice. And I find that's a really good way to learn all the reactions. There you go. So the next time you look up the structure of a medication, maybe, and we'll do that again this semester. You might see, okay, well, here's a syn diol, and now you'll know how to do it. So somebody asked me, where is sulfuric acid and heat on this list? Okay, so whenever they do a review of reactions, oftentimes there are reactions that get left out. So maybe a one-off or something like that. because the reaction where you just use sulfuric acid and heat with an alcohol and you end up with a Zaitsev alkene, that's actually covered in chapter 7. So you're expected to know those reactions as well. So if you go into chapter 7, and I don't know exactly where it would be, but it's probably somewhere towards the end of the chapter. Oh, jeepers. It's probably around section, yeah, somewhere around here. Yeah, it would be this one right here, okay? So if you take an alcohol and you treat it with sulfuric acid and heat, you end up with the E1 reaction, but you always end up with the Zaitsev product. I put here usually every case that we're going to look at, you're always going to end up with the Zaitsev product. Anyhow, there is no Zaitsev or Hoffman product with this particular alkene, but you get the idea. All right, there we go. So of course, for quiz 8, you're expected to know all the reactions for chapter 8, and you're expected to know the reactions from chapter 7. You're expected to know chapter 6 and 5 and 4 and 3 and 2 and 1 as well. But remember, when you go into the handout, or sorry, when you go into our modules, I should say, for our class, and if you look at the chapter 8 module, you'll see in there, there's a little PDF that's called Reagents 8, and you will be given that PDF. You're allowed to print that out and bring it in with you to the to the quiz.